This is part 2 of the integration by part. Let's look at example 4. Example 4. E to the x times cosine x. As I give you the lipid as an acronym, right? So to choose what is u and what's dv. In this particular case, the u is but e to the x, right? You see this one is polynomial, sorry, exponential, and that is trig. So if you have the lipid, right, e come before t, so you let u be e to the x. Okay, so we let u be e to the x in this case. So let's do the sign here. If u is e to the x, then dv is rest cosine of x dx. For u, you take a derivative. Du is e to the x dx. For dv, we find the antiderivative to look for v, and v is sine, right? Because derivative sine is cosine. Once you have that, plug into the formula. Again, uv minus integral of u. All right, so u is e to the x, v is sine x minus integral of sine x sine e to the x dx. Okay, so once you have the formula, apply the formula, you will always have a new integral to take in, right? So you, instead of integrate this, it's the same as e to the x sine x minus integrate this. But since we still have the product of sine and e to the x, a product of two functions, I cannot integrate directly. And since the product of two functions, trig and exponential again, right? Instead of e to the x cosine, that's e to the x sine. We got to use integration by part the second time. Okay. Now, as you can see, the u got to be e to the x one more time because the polynomial come before trig. dv is the sine. This time sine x dx. Take the derivative of u, that's e to the x. Find v by integrate sine. This time is negative cosine. Right? So apply the integration by part formula. So this integral right here, okay, I'm talking about this integral here, is now following this integration by part, u times v minus integral v du. See, u is e to the x, v is negative cosine, minus integral, v is negative cosine, and du is e to the x dx. Right, so that's equal to this. Now let's clean up a little bit. There's so many negative signs. You see the negative, if you distribute it in, negative turn into a positive. Here you actually have positive, negative, positive. Then you distribute a negative sign in. Basically you have three negatives, so turn into a positive. Okay, so as we clean up, multiplied in the negative sign, got e to the x sine to x, right? So that becomes plus e to the x cosine x there. And that becomes minus, this is e to the x cosine x dx. Okay, so that cleaned up is not too bad. Now, what happened is we have another integral to do, and this integral, unfortunately, is the same as the original integral. Right, it's the same. And originally, we feel like we got stuck. Why? Because you have product of two functions again. We cannot do it directly. And if we don't do directly, it looks like we use integration by part again. But what happened is when you apply negative by part, you get this one. Again, 4 times you get this one. So basically you end up with a cycle. You get to nowhere. We end up with the basically the infinite loop. Just look back to the original problem. However, we could solve this problem actually quite easily. Not easily, but with some trick, we can actually get this solved. So let me pull this original problem down so you can see. So this original problem, the integral that we have solved with, equal to this minus with the same integral we started with. Okay. Had we been able to integrate this, we had done, right? We can do that, and then we're done. But we couldn't because that ended up with the same expression we started with. So what can we do? Here's a trick we can use. But actually, if you remember back to the beginning algebra when you first learned variables, it's not hard to see if I ask you to solve, hey, can you solve this equation? Again, this had nothing to do with the problem we are working on. Just go back to this problem. How can you solve x equal 2 plus 3 minus x? See, that's simple algebra equations. Beginning algebra, actually. So how do you do? Well, remember we isolate the variable. I hope you can do it. Well, we're going to add x on both sides. We add x on both sides. So what we have is 2x on the left. 2 plus 3 got 5. That got canceled. What do you do next? Well, to get x by itself, you divide it by 2. Divide by 2, right? So we can divide it by 2 by 2. So x is 5 half. Done. Is it? Now you may wonder why we doing this. Checking to see if you can solve the equations in beginning algebra. Well, did you notice that this is almost the same as the one we just did? You see this one, the unknown. This is the unknown integral. Instead of unknown variable, unknown integral. Let's say this integral, we call it x, capital X, unknown variable, unknown x. But this is also the same, right? So that is unknown variable x. So if you have x equals something minus x, like what we did, how do you solve for x? Let me clear this. So you have x. This is x. So if you x equal this minus x, what will you do? Well, you add x on both sides. You add x on both sides. What do you have? You got 2x on this side, isn't it? And that's 0x, it cancel out. So that means you bring it over here, you would have 2x or 2 of this integral, right? 2x or 2 times the unknown integral. 2 times the unknown integral. Right? Add both sides. 2 times unknown integrals there equal this. And then again, what do we do when we get to 2x equal 5? You want to solve for x divided by 2. You want to solve for this unknown integral. You divide it by 2, divide by 2. Then this unknown integral is this over 2. Right? Divided by 2. And we're done. Divided by 2. What do you add the c again to the concept of integration? So it's going to be this over 2. This is called the solving for the unknown integral. It works when both factors integrate and differentiate forever, right? So like this one. Again, this one a little bit tricky, but if you've done it one more time, you can see it's very standard. Okay. Now, let me give you a quick guidelines on how to choose U and dV. I give you the limit, but it didn't explain to you why we got to do, like why we choose log versus inverse trig versus polynomial, exponential, and trig in that order. The reason is when you choose U, your goal is to make sure that the du or its derivative become easier to integrate than U. So because when you apply the integration by part, you have the second part, remember? So that's the same with U v mut integral v du. Okay, U dv. So when you apply it by part, you have a new integral. And this new integral, you got du. So if the du, the derivative is harder to integrate, that depletes the whole method. We want the integral, the new integral, easier to integrate. So that's why when you see the natural log is present, you want U to be natural log. Because I don't know how to integrate natural log, but if you take a derivative natural log is 1 over x, and I can integrate 1 over x. Okay. And also, oftentimes, you got to be powers of x or polynomial, because when you take the derivative, the powers go down. So this new integral will be easier to integrate than the original. Okay. Another reason, you see that in the limit, where this is U, this is U, this is U in that order, so that means the trig, the exponential are likely to be dv, right? If you choose that U, that will be dv. It's just because when you choose dv, you have to make sure that we can integrate dv easily. For example, if e to the x is present, right? We want e dv to e to the x, because when you let dv be e to the x, then I can integrate that e to the x easily. And oftentimes dv is sine and cosine, because this one I can integrate directly. Okay, and keep in mind that after integration by part, you should wind up with the integral that is easier to integrate. Okay, if you see something that is much harder and to integrate, you know you picked the wrong choice. Okay, so let's look at a couple examples here. Let's see how we go. I'm going to look at number 1 here, arctangents of 9x. Okay, so if you look at the example 1 here, finding the indefinite integral arctangent of 9x. Arctangent of 9x. So this one, there's a bit of, I know it's a common mistake here. When you again apply the integration by part, be aware that you identify the 2 parts of the functions of the integral. Okay. So what are the 2 parts? Notice this is the arctangent of 9x. Okay, so 9x is an argument inside the arctangent. So it's not arctangent and 9x are two part. It's one part. It's one functions. So that is one function. This is inverse trig. That's inverse trig arctangent. Okay. So when you have inverse trig, well, look like we're going to let u be that. But what will be the second functions? The second function, again, I don't have it explicitly. So think of that as the 1 as your second functions there. The 1 is a function and is regarded as a polynomial of degree 0. Okay. So with that said, for number 1, using integration by part, you will let u be the arctangent of 9x. That's one functions. Then your dv will be the 1 dx. Right? So when you have the u, and then you need to find the du, what's the derivative of arctangent? That's something you might want to review. The derivative of arctangent is 1 over 1 plus 9x squared. Okay, 1 plus 1 over 1 plus this in the function squared. Now, due to chain rule, don't forget that you need to multiply by the derivative of the inner function. Derivative of 9x is 9. So do not forget the 9 there due to chain rule. And then the other part, dv, you need to find the antiderivative. The antiderivative 1 is x, right? Derivative x is 1. Now, once you got the integration by parts are sorted down with the u and dv, we can apply the formula. So the integral that we have here is arctangent of 9x, right? So that is the v du here equal to u times v. U times v is arctangent of 9x times x. All right, u times v minus the integral of v du. So that's x times 9 in this quantity. I'll simplify that by putting x and 9s on the top of the fraction. So that'll be 9x over 1 plus, that's 81x squared dx. Right, so v du, 9 times x times 9, put on the top. So we got this. Okay. Now next, what will you do? You have a new integral. And once again, when you have the new integral, you're gonna figure out how to do that. Now, some usually suggest integration by part again, which we've done a couple of times, right? Not every time you're gonna do integration by parts. Why? Because this one, I don't even have the form I need. We have the product of 2 of the 5 functions that we have in limit. No, this is actually rational functions. So you back to 8.1, how we dealing with 9 point, polynomial function like this. Well, don't forget one of the rules that I said, you may want to look at the denominators, especially degree 1 over degree 2, so one less than the bottoms in terms of degree. We will take a derivative of the denominators, see what we have. So the derivative of 1 plus 81x squared is what? 0, right? Plus that is 2 times 81, so the 162x. So it looks like the derivative at the bottom is 162x there. So the derivative is 162x there, and I want 162x at the top. Okay, so recall that, and we could do that since it's off by a constant. And since this is off by a constant, we can do it by modifying. We can take the 9's out, times 162, divide by 162. Right? So let me write it down here. That one, let me rearrange. That's as x times arctangent of 9x. At the same time, I bring out the 9, right? I take out the 9. Remember, I need 162 to fit the formula. Then I leave my x on the top. And 1 plus 81x squared is there. Dx. I need 162, so times 162 and divided by 162. So you see that this is u prime over u, so that is the derivative. I mean u prime, yeah, u prime over u, derivative bottom, right? So that would become, the answer is x arctangents of 9x, and then minus 9 over 162. We can simplify that one. We can definitely simplify that one. Look here. We have this is natural log of the denominator is 1 plus 81x squared plus c. And I can simplify that to, right, that's 1 over, I think it's divisible by 9, so it will be 1, it's 18, I believe. All right, so that's 1 over 18, natural log of 1 plus 81x squared. And that is the answer. Okay, that is our answer. So box that one. Okay. All right. Now let's look at the next example. Look at the next example. Number 2. Of x to the 5th times natural log of x. Now this time, a bit different. This is the definite integral. The definite integral. Now with definite integral, notice that we would do or handle it the same way, except at the end you have to plug in upper lower limit, right? So all you need is to find antiderivative first. So for the problem like that, I often handle this as if it were a indefinite integral, right? So let's do this first. And once you have the antiderivative, I'm going to plug in upper lower limits at the end. Okay, so let's do that without the 1 and the 2. So again, this will be integration by part. We have two functions, polynomial and the log. Well, when I see the natural log, then your u got be natural log. It's the first choice for you, always, okay? So if u is natural log of x, then dv got to be x to the fifth. Don't forget the dx. Okay, and then you take the derivative of u, and that's 1 over x dx. And what's the antiderivative of x to the fifth? Antiderivative, remember, this add power at 1, so x to the 6 over 6. So our indefinite integral, remember we're looking at indefinite integral first, x to the fifth natural log of x dx is u times v, it's natural log of x, times x to the 6 over 6 minus the integral of x to the 6 over 6 times 1 over x dx. Right? U times v minus integral of v du. I guess for that one, this remaining integral we need to handle, although it has a product, right? You see there's a product. It's not a problem. Why it's not a problem? Because I could simplify. See, that is, well, I got simplified to x to the fifth, right? X to the 6 over x, and then there's a constant here. So if you rewrite, again, let me rewrite, putting that as 1/6 x to the 6 times natural log of x minus, and I also have 1/6 in front, integral of x to the fifth dx. Okay, so that is 1/6. So we have 1/6 times x to the 6 natural log of x minus 1/6. The antiderivative x to the fifth is x to the 6 over 6 plus constant, and that's finished. The problem, right? So that is the answer. Okay. Actually, I shouldn't box that one. So it's going to be Gendry is not. It's not my final answer. I will box my final answer. That is just the antiderivative. Okay, that's just an antiderivative. And don't forget that this is the definite integral. So the answer would be. So see, we have the antiderivative now, and I could use that information to finish. So this will be what? We have 1/6 x to the 6 natural log of x minus 1 over, I can believe that's 1 over 36. If you simplify, right, 1 over 36 x to the 6 x to the 6 there, and you plug 1 and 2, 1 and 2. So if you do that, I think the number is big. I'm not going to finish that, but you got an idea. When you plug 2 in, it'll be 1/6. That's 2 to the 6. What's 2 to the 6? I think is 64. 64 here. And natural log of 2 minus 1 over 36 times 64. And then you subtract, plug 1 in. Notice that the natural log of 1 is really 0, so the 0 is there. And 1 in, the 1 to the 6 will be 1 over 36, and you do the math there. All right, so leave it to you to finish the math there. All right, so for number 3, Now the number 3, you see there's an x squared inside of 3x, and that is what polynomial and trig, right? So number 3, you have polynomial and you have trig. So what do we do with polynomial and trig? Well, of course, you let u be x squared. But notice that in this problem number 3 here, there's a 2 square here, so you might have to use integration by part twice. Okay, but for number 3, we're gonna do with the shortcut, right? So remember what's a shortcut? What we call the tabular integrations. For the second power, I'm applying the integration by part twice. Sometimes we don't need this shortcut, but definitely with a third degree or higher, then we definitely have to use tabular integrations. So here anyway, I just want to review the technique. So when you're using the tabular integration method, I start with the x squared when functions. I let that be. So start with x squared here. Let's take the derivative. That is 2x, and the derivative 2x is 2. Derivative of 2, 0. Right? Keep taking derivative. So the next functions, the second function here is sine of 3x. Now remember that one, we're going to find the antiderivative. The antiderivative side is negative cosine. Right, negative cosine, right, the cosine negative sine. But don't forget that with chain rule, when you take a derivative, you have to take a derivative 3x, which is times 3. But with antiderivative, you divide it by 3 or negative 1/3. Now you take the antiderivative of this. What's the antiderivative cosine? Oh, that is sine. So you have negative sine of 3x. Sine of 3x. Again, derivative sine will be cosine. Now you have 1/3 here in front. But again, due to chain rule, instead of times 3, you divide by 3. So there's an extra 1/3 there. Or and I change that to 1/9. Okay. And you continue with the antiderivative of the sine is negative cosine. And so it turned into a positive cosine of 3x. But this time, again, 1/9, you have an extra 1/3, it becomes 1/27. Okay, 1/27. Now, with this done, then your integral now become, let me write it down here, the integral of x squared times sine of 3x is, now don't forget the sine would be positive here, negative, and positive. You go this direction. Okay, so what's the answer? X squared times this. So you would have x squared times this would be negative 1/3 x squared cosine of 3x. That times that. Then negative 2x times negative 1/9. So that become a positive plus 29 x times sine of 3x. And then you plus 2 plus 2 times 1 over 27. That's 2 over 27 cosine of 3x. And eventually, you'll finally be plus the constant. Okay, so that will give the final answer for this problem. Okay. Right, so I'll skip the last one, number 4 here. For you, it's an exercise, right? All right, so number 4 is similar to number 4 up here. All right, that finished 8.1.